Good morning. We are going to start on permanent magnet brushless DC motor drive in today's class. The structure of a permanent magnet brushless DC motor is somewhat like this. This is the cross section. So if you are looking at the entire thing, it is as though the cylinder is extending into the bore. So in the cross section, you can see that this is the rotor. So the rotor core is here, which may be made up of iron. And on the surface, you will see the permanent magnets mounted. So I can say this probably is North Pole and this is going to be the South Pole. What is mounted on the surface, you can see the blue colored one, what I am shading now, that is actually the South Pole. The same way this is going to be the North Pole. So roughly this is extending over almost 180 degrees. Each magnet is extending over almost 180 degrees. So you can say if you look at the air gap, currently A is completely facing North Pole and A dash is completely facing South Pole. And if I am going to have this magnet, if I say that this is theta equal to 0 degrees, this is corresponding to rotor position theta equal to 0 degrees. And let's assume the rotor is rotating in this direction. It is going to rotate in this direction. So if the rotor is rotating completely by 90 degrees, this point, whatever we are talking about, this would have gone to the beginning portion and this end of the magnet would have reached this portion if it had rotated by 90 degrees. Still, completely A and A dash, for example, A will be still under the influence of North Pole and A dash would be still under the influence of South Pole. To show this, I should say if this is the rotor cross section, I am going to have from this point until almost this point, now it is going to be North Pole. And from this point until this point, this is going to be South Pole. So I'm going to have this as theta equal to 90 degrees position. This is going to be theta equal to 90 degrees position. So if you really look at it, I'm going to have A sitting here and some portion of B dash would also have come here. Basically this some portion of B dash also would have come here. So I should have here shown this should be B dash. And similarly, I will have definitely some portion of A would be here. And I'm going to have probably this B, some portion of B, which is also the dot, that would also be here. So this is how theta equal to 90 degree position will be. Then this moves further another 30 degrees. This end, whatever I am talking about, so this end that I am talking about, that would have reached almost this point. This end would have reached this point. So due to which I am going to have, so if I draw the flux position, basically, let me draw it with respect to rotor position. So let me draw the vertical line first. So let us say this is the axis which is actually corresponding to the flux. And let us say this is going to be theta. Okay. So I'm going to draw with respect to theta. I'm going to draw first of all whatever is the flux position. So let me first of all draw this as 180 degrees and this as 360 degrees. And I can divide this into 3 portions so that it becomes essentially 180 plus 60, 240, 240 plus 60, 300. So this is going to be 300, this is going to be 240, this is 60, and this is 120. And you can see that for A phase, right from theta equal to 0 degree until theta equal to 120 degrees, all three conductors of A phase, they are going to come under the influence of North Pole. Or three conductors of the A dash phase, those are going to come under the influence of South Pole. So until 120 degrees, it is at the peak of, let us say, positive flux. If I am talking about that is the three conductors of A, if they are coming under the influence of North Pole, I'm going to call that as positive flux. So if it is a constant flux and if the rotor is rotating at constant velocity, I will also have the induced EMF. So the induced EMF in A phase conductor is going to be K times whatever is the flux of A phase multiplied by whatever is the velocity at which the rotor is rotating. So I can call this as EA. It is going to be EA, which is actually constant from theta equal to 0 to theta equal to 120. But between 120 and 180, if this is moving further, you are going to see that 120 degree point is somewhere here. That is where the end of this North Pole would have come here. Then if you go beyond that, part of A conductor is going to be under the influence of North Pole, and part of the A dash conductors are going to be under the influence of South Pole. So which means you are going to have some amount of cancellation between what is excited by North Pole or what is influenced by North Pole and what is influenced by South Pole. But the moment 180 degrees point is achieved, you are going to see that completely EA has become negative, which means it has come under the influence of South Pole. So from 180 to 300, it is going to be under the influence of South Pole. The conductors, three conductors of A phase are going to be under the influence of South Pole. And from 300 to 360, again, it is going to reverse itself and again, it will become positive at 360. So this is going to be the waveform corresponding to EA, that is induced EMF in A phase. And this wave shape is trapezoidal in nature because of the shaping of the magnet and air gap and things like that. So permanent magnet brushless DC motor is a trapezoidal flux machine. The flux is going to be trapezoidal in nature. The same thing holds good for B and B dash, but only thing is they are going to be displaced by another 120 degrees. So I can show it as though at 120, I am going to have the peak value of flux as far as B phase is concerned, and that is going to be from 120 to 240. And 240 to 300, 300, it is going to come down like this. Then from 300 to 360 and 360 plus 6420, or I can say on the other side, it will come out like this. From 0 to 60, it will be negative. And from here to here, it will actually go up like this. So this is going to be EB. So this will be the waveform corresponding to EB. And EC will be again another 120 degrees shifted from EB. That means from 240 onwards, it is going to become peak until 360. So this will be again for 120 degrees and it will come down like this. And here it will come down from 360 like this. So this is going to come down like this. So you would see that A phase, B phase, and C phase, at least one of them definitely has the peak of the flux at different instants of time. That is 0 to 120, EA has the peak. 120 to 240 EB has the peak, and 240 to 360 EC has the peak. The same way in the negative side, you would see 0 to 60 degrees EB has the minimum value of back EMF, and 60 to 180 EC has the minimum value of back EMF, and 180 to 300 A has the minimum value of back EMF. So if hypothetically we assume that wherever I am going to have EA to be maximum positive, at that point, if I allow IA to carry maximum value of current like this. So this is going to be IA positive. And let us say during this portion, I want IA to carry the reverse current. So if I say that I'm going to have IA to carry the reverse current during this portion, I am going to see normally that EA times IA is the power. So I will have power delivered by A phase. That will be basically EA times IA from 0 to 120 degrees. And I'm going to have minus EA times minus IA from 180 to 300 degrees. So in either case, it will be positive. EA times IA will also be positive, minus EA times IA will also be positive. So ideally, if I try to pass a current in A phase winding in the positive direction from 0 degree until 120 degrees, and in the reverse direction from 180 degrees until 300 degrees, I will have basically torque or power that is developed in the positive sense. The same way, if I try to pass a current which is corresponding to B phase or C phase, for example, if I try to pass a negative current from here to here completely, if I try to pass a negative current in C phase, and if I'm going to have literally zero current until this point, so I'm going to have the positive current again flowing from 240 until 360 degrees. So this is, for example, I'm going to have this as 60 degrees. This is going to be 180 degrees. And this is going to be 240 degrees. And this is going to be 360 degrees. So if I have IC as positive from 240 to 360, and IC as negative current from 60 to 180 degrees, then I would be again delivering a positive power from C phase, which will be corresponding to either ECIC or minus EC times minus IC. Now, if the same way, if I have B phase current somewhat like this, so B phase current will be from here until 120 to 240. So I'm going to have literally B phase current somewhat like this. So this is going to be B phase positive current. Whereas B phase negative current is from 300 to 360, either here, and also 360 to 420 or 0 to 60 degrees. So this is going to be 60 degrees. So if I pass B phase current like this, again I will have the power to be EB/IB or minus EB times minus IB. But at every 60 degree instant, if you look at it, so during this portion, let me probably draw this further. And let me show exactly what happens in terms of the current or power. So I should say from 0 to 60 degrees. I have basically IA positive and IB negative. And if I try to look at 0 to rather 60 to 120 degrees, I am going to have IA positive, whereas IC is negative. And 120 to 180 degrees, I am going to have IB positive and IC negative. And 180 to 240 degrees, I am going to have IB positive but IA negative. And after that, 240 to 300 degrees, I'm going to have IC positive and IA negative. And 300 to 360 degrees, I'm going to have IC positive plus IB negative. So this is extremely similar to what had happened in our three-phase converter or three-phase inverter in 120-degree convection mode. This is what we had written earlier. So in a PMBLDC motor, if we want to pass currents like this, that is IA should be positive from 0 to 120 degrees and it should be negative from 180 to 300 and so on, three-phase inverter in 120-degree conduction mode will be able to do the job. So if I again use the same inverter circuit, what we had talked about earlier, so let us say I have one phase here with two devices like this and feedback diodes also. So let me show the feedback diodes as well. And similarly, I have second phase, which is corresponding to maybe B phase. And I'm going to have this as, the diodes, feedback diodes for these two devices. And let me show the third phase whose leg is somewhat like this again. Okay. Now, if I am assuming that this is excited by the DC voltage, which could be a rectified voltage from a three-phase supply using thyristor converter or anything else, or it could be a battery. If we are talking about electric vehicle, generally PMBLDC motors are used in two-wheelers very commonly. So in those cases, the battery is going to provide the power source. So that is going to be the power source. So these are the 6 devices that we are talking about with respect to the three phases. So let me number them the same way like what we had done. This is S1 and this is going to be D1. This is going to be S4. This will be D4. This will be S3 and this will be S5. So this will be D3 and this is going to be D5. And this will be S6 and D6. And this will be S2 and D2. So I am going to take out the connection somewhat like this. So I'm going to take the connection out of this, which is going to A phase. I'm going to take the connection out of this, which is going to B phase, and this is going to C phase. So if I assume that this is going to be A phase winding, and this is C phase, and this is going to be B phase. So I can connect here, let us say this is A, and I can connect this to the B phase like this, and I can connect this to the C phase. So this will be B dash, the other end of the winding. This has to be C dash, and this has to be A dash, and this is the neutral point of the PMBLDC motor drive. Of course, the rotor will have the magnet. If I say this is the rotor, I'm going to have the magnet put on the surface like this. So this is North Pole and this is going to be South Pole. So this is the way generally the magnet is going to be put up. So this is North and this is South Pole. Okay. Now from the devices, I should be able to say if IA is positive, I am going to have essentially 6 and 1 conducting here, 1 and 2 conducting here, 2 and 3 conducting here, 3, 4 here, 4 and 5 here, and 5 and 6 here. Again, 6 and 1 will repeat after 360 degrees. This is going to be the conduction sequence. And if I look at 0 to 60 degrees, I am going to have the power to be EA times IA plus I will have minus EB times minus IB. So that is EB times IB. So this will be essentially 2EI, whatever is the current that is flowing through any of the phases, the current will be returning through the other phase. So the induced EMF multiplied by that current gives me the power. So it will be twice EI. Similarly, from 60 to 120 degrees, the power is going to be EAIA plus minus EC times minus IC, which is ECIC. And 120 to 180 degrees, I'm going to have the power to be EBIB plus ECIC. And 180 to 240, it is going to be EBIB plus EA times IA. That is minus EA times minus IA. 240 to 300, it is going to be ECIC and minus EA times minus IA. So this will be ECIC plus EAIA. And 300 to 360 degrees, it is going to be 300 to 360 degrees. It will be 5 and 6, which is ECIC plus EBIB. So these are going to be the power. Basically, what is created out of the motor and which is imparted ultimately to the mechanical loop. So if I try to look at the power, in every 60 degrees, it is going to be 2 times EAIA. So it will be literally a constant. So the power is going to be a constant, no matter what. It will be 2 times EI per phase. That is what is going to be the general norm. So when we control the PMBLDC motor drive, again, the rotor position becomes extremely important. Only if the rotor is in the position of 0 to 60 degrees, I should be firing 6 and 1, both of them. If I'm going to have 60 to 120 degrees, I have to fire. So I can write here very clearly what are the devices that are fired. So I'm going to have 6 and 1 fired here, 1 and 2 fired here, 2 and 3, 3 and 4, 4 and 5, and 5 and 6. This is how they are fired cyclically. So I need to have the rotor position information even in the case of PMBLDC motor drive. So how do we get the rotor position? So rotor position is generally ascertained with the help of generally rotor position encoder. In the drives course, we had taken a look at this earlier, but I am just reiterating this. So what we generally see in the form of rotor position encoder is, let us say this is the shaft to which the motor is coupled. So the motor is sitting here. So this is the motor. Okay. So to the motor shaft, I am coupling basically a shaft, and along with the shaft, I'm going to couple another disc. And in the disc, if I just make this with wood or some kind of Hylam board or whatever, I am trying to carve some holes along the periphery of this disk. I'm going to carve some holes, let us say something like this. So if I carve, for example, 360-degree holes, for every degree, I would have one hole, basically. So I am looking upon this as, let us say, this is the disk, and in the disk, I am carving holes somewhat like this, right after one another, and depending upon how many holes I have carved, there will be so much of displacement between two holes. If the shaft displaces by, let us say, 1 or 2 degrees, then it would have moved past 1 or 2 holes here. Now, apart from that, if I say that maybe North Pole is beginning at this point, or North Pole midpoint is somewhere here. So along that, I'm going to carve one more hole. So let us say I carve one more hole separately at this point. So this is corresponding to theta equal to 0 degree. Now, on either side of the hole, I'm going to have one LED. So let us say I have LED on one side from which the light will be emitted whenever it is given a power supply. And if a hole is intervening between the LED and a phototransistor will be on the other side. So here is the phototransistor on whose base this light will be falling. So if a hole is intervening between the LED and the phototransistor, then the phototransistor will conduct because it will have a base drive. If not, it will not be able to conduct. So I am going to look at this somewhat like this. This is my LED, which is given maybe a 5-volt supply or something with the help of a small resistance intervening between the power supply and the LED so that the current is limited somewhat. And this is going to push the light or focus the light onto the base of a phototransistor. And in between, if there is a hole, I would see that the phototransistor is able to conduct. If not, it will not conduct. So now let us say this is also connected to some 5 volts or some VCC, 15 volts or something like that. Now, if I look at what is the output here, whenever I'm going to have the transistor in off condition, then the entire VCC will come out. Whereas whenever it is going to be in on condition, and it will be on only if a hole is intervening between, the LED and the phototransistor. So at that point, I'm going to have literally 0 volts or whatever is the VCE of the transistor that will be coming, 0.7 volts or something. So I'm going to have literally something like this coming out of this transistor. So whenever this is not conducting, or when the light is not focused on the base of the phototransistor, at that point I'm going to have plus VCC. If not, I will have 0.7 volts whenever it is conducting. So this is when transistor is conducting, or light is focused on the base of this transistor. So I am going to get continuously pulses like this. If there are 360 holes, I will essentially get 360 pulses like that. So I can say this is corresponding to theta equal to 0. So when both pulses are coinciding with each other, that is corresponding to 0 degree. That is this pulse, if I may call this as P1, and if I may call this as P2. So this is P1 and this is P2. When they are coinciding with each other, that is where I'm getting theta equal to 0 degree. So I will keep a tab on, where theta equal to 0 degrees occurring. And at that point, I should be firing according to this 6 and 1, devices 6 and 1. Then when I have counted 60 pulses, if there are totally 360 holes that are carved here, when I have counted 60 pulses, 60 degrees are over. At that point, I have to fire 1 and 2. So I should be able to count the pulses here, from which one, I should be able to get what is the rotor position relatively with respect to P1. And second one, I should be able to even get the velocity, because if 360 degrees are traversed within so many seconds or so many milliseconds, then I should be able to calculate very clearly what is the revolutions per minute. So rotor position encoder will be able to sense the position clearly, position sensing, as well as it will be able to give clearly revolutions per minute or speed as well. Both can be inferred. So I can say if 360 holes or 360 pulses are traversed in 6 milliseconds. For example, I'm arbitrarily just saying this. So in which case, one revolution in 6 milliseconds. So I should say 6,000 revolution in 6 seconds. So 60,000 revolution in 60 seconds or 1 minute. So I can right away say this is 60k RPM. That is the speed of this particular motor at this point in time. So rotor position encoder, this is like a mechanical encoder because we are making an arrangement externally. So this is a mechanical position sensor or speed sensor. This will be able to find exactly which devices have to be fired at what interval, provided I have had the arrangements properly made. In an electric vehicle, this is going to be a little difficult. That is the reason why we generally go for sensorless techniques, because it can shake, it can move a little bit. Sensorless position estimation. This is generally adopted in many of the arrangements where it will not be a very stable arrangement to have a mechanical encoder. So in that case, what we tend to do is, if I know what is the voltage, terminal voltage, what I have applied, minus, I have sensed the current also, I times R, minus whatever is L di by dt. I should know what is the kind of inductance that, the winding is possessing at this point. So that will give me what is the value of voltage or back EMF. So either EA or EB or EC for that particular phase, from which we should be able to say whether if EA is at its maximum, then we are going to fire 1. If EA is at its minimum, we are going to fire 4, and so on. So this will be repeated generally, depending upon the back EMF estimation. So back EMF estimation can be done using terminal voltage and current measurements. So if I do that, I should be able to infer what are the values of back EMF, from which I should be in a position to fire the appropriate devices. It should not be an issue. So overall, if I try to look at the control configuration for a PMBLDC motor, so it will be somewhat like this. First thing is, again, the aim is to maintain the speed at some reference value, and that has to be compared with what is the actual speed value. These two are compared, and this should go to a speed controller. So the speed controller again can be a PI controller, PID controller, fuzzy logic controller, and so on. So this is the error in the speed. So that is sensed first. And what is coming out of this? We'll set the torque value. How much should be the torque value to bridge the gap between the reference speed and the actual speed? So this is going to set, what is the torque value. And again, I can do TE minus TL and what should be the accelerating torque. All those things I can find out. Accordingly, I can decide how much should be the value. So let us say this is the electromagnetic torque and this has to be compared with the load torque. In fact, I can call this as the accelerating torque because this is indirectly whatever is the difference between the two speeds. And we said already J d omega by dt equal to TE minus TL, which happens to be the accelerating torque. This is what is going to accelerate the machine. So these two have to be added ultimately to arrive at what is the electromagnetic torque that needs to be generated by the machine to bridge the gap as well as take care of the load torque demand. Now this is electromagnetic torque reference. Now using this, I should be able to calculate the current. What is the kind of current? Because the flux is already fixed by the permanent magnet that is sitting in the rotor. So I should be able to definitely look at what is the kind of current that will be needed in every phase. Now from here, the current value has been arrived at. Okay. And I have to combine this with which phase has to be fired. So let me try to put this as commutation logic. So commutation logic will mainly require rotor position information. So theta will be needed here. If theta is between 0 and 60, we already said that we are going to have in all probability 6 and 1 fired. If it is 60 to 120, we are going to have 1 and 2 fired. So accordingly, theta will decide whether I'm going to have IA as positive and IB as negative, or IB as positive and IC as negative, or IC as positive and IA as negative. All these things will be decided. So this will be IA star, this will be IB star, and this will be IC star. So these are going to be the three-phase current that we are looking at. Now we are going to have a current controller here. I am going to call this as hysteresis current controller and I will explain it shortly. So this is the hysteresis current controller, which is going to combine or make a decision based on the values of both IA star, IB star, IC star, and the actual value of IA, IB, IC. So I will have IA, IB, and IC, the actual values coming here, which are fed to the hysteresis current controller. Now, what is coming out of this actually is going to decide the pulses which are actually going to the 6 devices of the inverter that we talked about just now. So this is the inverter which is feeding the PMBLDC motor drive stator winding. So we are essentially looking at these pulses going to the VSI. So the VSI 6 devices are going to be fired based on the pulses that are coming out of the hysteresis controller. And of course, VSI should have the DC supply connected here. And from here, I'm going to have the 3 phases whose currents are sensed. And that 3 phases are going to be connected to PMBLDC. DC motor. So this is connected to the 3-phase PMBLDC motor. Now, this motor is coupled to the load. Let us say maybe the two-wheeler or whatever. And we are going to have basically the currents that are coming from here. This is C phase current. This is B phase current. And this is going to be A phase current. So current sensing is done from here. And this PMBLDC shaft is connected to, let us say, an encoder or some kind of position sensor. So the position sensor output, what is coming out is theta. This is theta, which is going to the commutation logic. In fact, whether I want to rotate the motor drive in the positive direction or negative direction, in fact, even that can be given in the commutation logic. So even direction can be given properly in the commutation logic. And here if I differentiate, that is delta theta divided by delta t, that will be giving what is the actual speed. So this completes the loop of PMBLDC motor drive. Control configuration is actually, clearly specified here. And commutation logic is the one which takes care of which are the devices to be fired and what direction the motor has to rotate. These two things are decided based on whatever is the command that is position sensor. So the position sensor, which is mechanical in nature, that can be replaced by terminal voltage and terminal current sensing. So here we have sensed already terminal current, but terminal voltage also needs to be sensed, and from which you can subtract Ri and L di by dt drop ultimately to arrive at what is the value of E. So that will the back EMF, once it is determined indirectly, that can also determine the flux value, which will indirectly tell us which devices are to be fired. Okay. So this is the control configuration of the PMBLDC motor drive. Only thing I would like to explain now is the hysteresis current controller. So what is a hysteresis current controller? So let us say after calculating the torque and everything, I have arrived at a value of current which is 10 ampere. So I don't want the current to go beyond 10 ampere. I don't want the current to be much less than 10 ampere either. So actually speaking, let us say at this point in time, I am expecting that the current should remain constantly at 10 ampere in A phase. So I want A phase current to be 10 ampere from 0 to 120 degrees. So if you really look at it, I'm going to see that this is A phase leg. And I'm going to have this as the A phase leg consisting of device number 1 and device number 4. And I'm going to have this connected to the positive side of the supply, power supply, and this connected to the negative side of the power supply. And from here, I am going to have A phase winding connected. So if the current is going in this direction, I call that as IA positive. So 0 to 120 degrees, current has to be kept at, let us say, plus 10 ampere. So if I initially say that the current is somewhere here, maybe the current is starting from 9 ampere or something like that. Because of which, if I fire S1, the current will start increasing because it is connected to the positive leg of the positive terminal of the DC supply. The current has increased. At this point, I am sensing the current. and I see that the current is exceeding 10 ampere, maybe I'll give a band. It should not go beyond 11 ampere and it should not fall below 9 ampere. So I can say I will allow a change of 11 ampere on this side and 9 ampere on the other side. So if it has exceeded 9 ampere, I'm going to turn off this S1. The moment I turn off this S1, the current is still flowing in this direction and the current cannot be abruptly interrupted. So automatically D4 will take over. So when D4 takes over, please note that I'm going to have the negative terminal directly connected to this A phase's original terminal, which was connected to the positive one through S1. So the current will start decreasing. So I will see that D4 is conducting for some time, and once the current becomes less than 9 ampere, again S1 will be turned on. So because of which you may not see a constant value of current, but the current is fairly maintained close to 10 ampere. So wherever the current is increasing, I would say S1 is conducting. Wherever the current is decreasing, I would say D4 is conducting. So S1 and D4 alternately conduct to maintain the current exactly close to 10 ampere. How quickly the devices switch in and switch out, it depends upon two things. How frequently sampling is done. It depends upon that and it is being compared. And the second thing is, what is the delta I value? Here we have said 10 plus or minus 1. So I plus or minus delta I. This is what is going to be maintained. What is the delta I value chosen? So these are the two things that are going to decide how frequently the switching is done. If the band is delta I is really, really small, you may see something like chattering. So it will go on, switching in and switching out S1. And unless the devices are good enough for fast switching, it can result in the problem with the inverter. It can be completely short circuited. One leg can be short circuited and so on. So we don't want that to happen. So we have to choose the delta I value and sampling frequency very judiciously when we are running a PMBLDC motor drive or SRM drive where we want to maintain the current at a particular value. In fact, even in sinusoidal currents, you can have something like a hysteresis controller. So what we mean by hysteresis controller in that particular case is, if this is going to be the sinusoid that I want, which is supposed to be the reference current, I may actually put a band on the plus side as well as minus side. So I may try to put a band like this. So I will say that the current should not go below some delta I and it should not go above some delta I compared to the reference current. So this happens to be the reference current, and these happen to be I plus delta I and I minus delta I. So let us say at present my current is somewhere here. So it is just on the verge of going into beyond the negative limit. So at this point, if I switch on, for example, S1, then I'm going to have an increase in the current. At this point, it is hitting the limit, so I will switch off. So the diode will conduct. So this will happen repeatedly. So it is not exactly sinusoid, but it is close to a sinusoid. That's what happens when I am looking at a hysteresis current controller being employed for current control, whether it is in a sinusoidal PWM inverter or whether it is to maintain a current at a particular value, maybe 10 ampere or 15 amperes. Okay, so this becomes a part and parcel of our motor drive control. So in a two-wheeler, in an electric two-wheeler, if we are looking at PMBLDC motor, this is generally controlled without a position sensor. Most of the times we would like to have a sensorless control where the terminal voltage and terminal currents have to be measured, and from which the back EMF is estimated, and from the back EMF theta can be estimated successfully. And based on that, a current controller will ensure that the required current is passed through the PMBLDC motor drive so that we are able to achieve, a good amount of torque for the machine to be, the vehicle to be propelled. Okay. So with this, we are concluding special motors. We had seen stepper motor. We had also looked at switch reluctance motor drive, which is an extension of variable reluctance stepper motor. And finally, we concluded this with PMBLDC motor drive. There are huge number of research papers that have come up in both SRM as well as PMBLDC because of the variations in the current we see. The torque would correspondingly be pulsating. We see in PMBLDC motor drive that EA is proportional to omega m. And if you look at the torque which is power divided by omega m will be proportional to current. If we assume that back EMF is proportional to speed and flux, and if the flux is a constant, we are going to say electromagnetic torque is proportional to the current. So the characteristics are very similar to a normal DC motor, and that is the reason we are adopting a nomenclature which is very similar to a DC motor. Although how we are exciting the motor is using an inverter, voltage source inverter. So we call this motor as a PMBLDC motor, DC motor. That is because back EMF is proportional to omega and torque is proportional to current. That is the reason we are calling this as a DC motor. So PMBLDC motor finds huge number of applications now in electric vehicles, especially for power windows and for the wiper motor and so many other things. We are trying to use PMBLDC motor because of the torque pulsations being minimized and its better efficiency. But of course, the deterring factor is use of permanent magnet itself. Okay. So much so for special machines in the case of drives. Okay, I would like to include or show a few simulations I have done for both PMBLDC motor drive as well as for the switch reluctance motor drive. I had given the reference speed to be about 6,000 RPM. So you can see that the speed is slowly increasing and it is reaching 6,000 RPM eventually. And when the speed is lower, each of the phases conduct for longer duration. You can see that the width of each of the reference Hall pulses keep on decreasing. So this is the position sensor signal. So two phases position sensor signals have been shown. Hall A and Hall B, they are specified as Hall effect sensor A and Hall effect sensor B. The third phase will actually come for another 120 degrees. So each of these position sensors occupy duration of 120 degrees in the positive half cycle as well as negative half cycle. And you can see that for 60 degrees almost it is at zero. A similar thing is happening in terms of the actual current also. You can see that the current is for one of the phases, the blue color one, that is IA, that is actually looking like this. And you can see a zero current period here. and then the negative 120-degree duration, and that is repeating itself. Okay, the same thing is happening with respect to IB, which is actually green colored current waveform. And this is the electromagnetic torque, which is exactly taking the wave shape of whatever is the current. So you can see very clearly there are oscillations in the electromagnetic torque that is not reflecting so much in the speed, because the inertia is somewhat acting like a filter, and that is filtering the oscillations out from the speed response. So this is the simulation of a PMBLDC motor drive, three-phase case, and you can you can see the responses are as expected normally. Let me go over to switch reluctance motor drive now. Excuse me. This is a 6x4 SRM motor drive, the model that is available already in PSIM. So you can see that the currents, what we see here, are for two phases. The third phase current would have come somewhere here. The first phase and second phase, the currents are looking like this. And these are the position signals again. You can see very clearly that we are having the first phase and the second phase. They are staggered from each other by certain angle, and correspondingly wherever we are having the red phase or A phase increasing, the position is increasing. At that point you can see very clearly the current is exactly coinciding with this, and the blue current is actually coinciding with this. When there is a overlap between the red phase and the blue phase, that is where you would see that the torque is higher than the level torque. See, if there had not been any overlap, then only one phase torque could come out. Whereas when there is an overlap, two phase torques are added together, and wherever there is overlap, you would see correspondingly that there is a bump in the torque. There is a higher torque that is coming up. So the torque, what we see is summation of all three torques together. And the speed here, you hardly see any oscillation again, because the inertia is smoothing out the oscillation. And the green color, whatever is shown, that is going until 360 degrees and it is coming down again. So every rotation, at the end of every rotation, that particular counter is set back to 0, and it is going from 0 to 360 degrees completely. So this is the position signal with respect to the rotor rotation, whereas these are the position signals corresponding to A phase and B phase. C phase position I have not shown here at all. So within 360 degrees, you can see this is one peak for the phase A, and this is another peak. This is the third peak, and this is the fourth peak. So because there are four rotor signals, you can see repeatedly this is coming out like this. And you can see this is corresponding to the next phase, and there will be again four peaks for the next phase as well, but it is staggered from the first phase by about 15 degrees or something like that. So this is what is basically seen here. Okay, so this is the simulation corresponding to switch reluctance motor drive. This is just to give you a feel for how the waveforms, the position sensor signals, all of them look like. Okay. So we had seen the special electromechanical devices or stepper motor, switch reluctance motor, and PMBLDC motor in this lecture. So I'm going to conclude this course with a few concluding remarks. So I would say we started this course with what is an electric drive. Then we were trying to look at what are all the different components in an electric drive. Then we looked at systems with gears. So we actually looked at various systems that are involved in the coupling of the motor with the load system. So we looked at the gear arrangement and translation to rotational converter and vice versa. Okay. And we try to calculate basically how we can calculate the equivalent torque and equivalent moment of inertia and things like that. So I would say MI and torque calculations. These are the things we initially looked at. Then we also looked at determination of moment of inertia and how it plays a vital role in deciding the time that is required for oscillation. Then we also looked at load equalization. That is, if there is a huge difference in, load requirement, then, how we can equalize it by having a flywheel and releasing the energy from there, at least when there is a shortfall of electromagnetic torque produced by the motor drive. Then we also looked at heating and rating, that is thermal calculations we had done. So all these things, and we looked at, of course, stability, steady state stability, and so on. So with this, our general aspects of electric drives was concluded. And after that, we ventured directly into DC motor drive. So in DC motor drive, we mainly concentrated on, of course, starting, speed control and braking. So in starting, of course, resistance-based starter, that is what we started with. And later on, we also said that rectifier, which is fed with an auto transformer, or a controlled rectifier, that can also be used to give a smooth start as far as starting is concerned. And in speed control, we mainly looked at rectifier fed. So in rectifier fed, we specifically looked at single phase as well as three phase, and fully controlled and semi-controlled configurations. We also looked at dual converter. We briefly visited commutation overlap and its effects on overall performance of the rectifier. And after that, we went into chopper fed configuration, in which we mainly looked at buck converter and boost converter, both of them, in terms of how they can be used for speed control and regenerative braking respectively. Finally, we looked at braking also, and in braking, we looked at all the three types of braking, namely dynamic braking, regenerative braking, as well as reverse current braking or plugging. So all of them we looked at. After this, we ventured into induction motor drive. So in induction motor drive, we looked at the basic principle, equivalent circuit and all that. In this also, we looked at various starting methods, inclusive of AC voltage controller being used for soft start, star delta starting, then impedance starting, and so on and so forth. After that, in braking, we looked at both regenerative braking and dynamic braking. In dynamic braking itself, we looked at 4 different kinds of dynamic braking, like capacitor braking, then DC dynamic braking, AC dynamic braking, zero sequence braking, and so on. And in plugging, reverse current braking or reverse phase sequence braking, that also we saw. Then we ventured into speed control. In speed control, we looked at both rotor side control for wound rotor induction motor and stator side control for squirrel cage induction motor. So in speed control, we looked at pole changing very briefly. Then we looked at V by F control mainly for squirrel cage induction motor. We also looked at AC voltage controller for whether squirrel cage or wound rotor induction motor. Then we also looked at field oriented control and direct torque control using inverters. And these are voltage source inverters. Then we also looked at current source inverter fed induction motor drive control. Then for rotor side control, we looked at both rotor resistance control and slip energy recovery. So after this, we came over to synchronous motor. In synchronous motor, again, we had looked at starting. So how starting can be implemented using pony motor or V by F control and so on. We looked at, in fact, various types of synchronous motor like wound field rotor. We looked at permanent magnet rotor and we looked at reluctance rotor. We derived the torque expression for these kinds of rotors. We also looked at the phasor diagram for wound field rotor, especially with reluctance principle. And we came over to dynamic braking of synchronous motor. In fact, when we were discussing the general principle of synchronous motor, we also looked at V and inverted V curves. We looked at the torque expression. We talked about hunting oscillation. Then when we came over to speed control, in speed control, primarily we looked at two different kinds of speed control schemes. One is true synchronous mode, and the second one we looked at was the LCI fed self-controlled synchronous motor drive. And finally, before concluding the course, we looked at special machines. So as I just mentioned in the beginning of this lecture or concluding remark, in special machines, we primarily looked at stepper motor, and as an extension of variable reluctance stepper motor, we looked at SRM, switch reluctance motor drive, SRM drive, and finally, we looked at PMBLDC motor drive. So I had tried to give simulations and other explanations wherever I can. And if you have any questions, you are free to write to me in my Gmail account. That's not a problem. Thank you so much for paying attention. And it has been a great encouragement for me to look at so many subscribers. Thank you once again for supporting this endeavor.